Thank you very much. And again, as he said, we'll have the Q&A later in the next session. So we have finally the last talk of the session. So it's which will be delivered by Professor Kosan. So he's right now working in the Department of Chemical Engineering and Applied Chemistry at Chungam National University. Professor Ro received a bachelor and PhD from KAIST in 2011 and 2017, respectively. And now he's working on applying computer-aided tools to the design and optimization of emerging chemical and biotechnological processes. So thank you very much.
Okay, thank you for your warm introduction. Also, I appreciate the organization of this great workshop next to the beautiful West Lake in Hangzhou. So today I'm going to talk about a kind of the scheduling problem, which is not just a simple scheduling problem, but which is associated with the design problem too. So as a young faculty member, as a young assistant professor, I would like to take this opportunity to PR myself. So as introduced beforehand, I did my PhD at KAIST under the supervision of Professor J.B., who is currently at University of Southern California. And while I'm studying my PhD, I visited DTU to collaborate with Professor Gani in the year of 2014. So I worked on the carbon capture and utilization problem there. After I finished my PhD, I moved to another European country, Germany, to work with Professor Alexander Missos at RWTH Aachen University to work on the flexible operation problem, which would be the main topic of today's presentation. And then in the year of 2021, I came back to my home country. Next to the university, I got my PhD at Chungam University, and now I'm enjoying teaching and researching to my students. So demand side management is the key word of my talk today. So as more renewable energy resources are penetrating the power grid in Europe, the price of the electricity and also the supply of the electricity is fluctuating over the time a lot. So in the case of the Germany, as you can see here, it was in 2018 already, like almost 6 years ago, was at the time already the fluctuation of the spot electricity prices was really strong because of the huge amount of the generation of the solar and wind energy. So why this is a problem? Because this causes imbalance between the supply and demand in the power grid that would cause a very serious problem in the whole country. So there are several solutions to defeat this problem, and one of the solutions is the demand side management, or DSM for short. So for instance, during the time when the demand is high, some players in the power exchange market could reduce their power demand, or they could divide their demand to the period when the demand is not really much. And there are also different types of strategies to employ the DSM. So there are two representative cases where the DSM could be beneficial. So first one takes place in the balancing market. So I took this figure from this website where this the gauge indicates the current frequency of the European power grid. So it should stay around the 50 Hertz, as many of you already know. But if there is more demand or if there is a less demand, then this arrow moves up and down. So in order to avoid much deviation from our standard level, someone needs to reduce their power load, or someone needs to increase their power generation, or vice versa. So if you participate in this balancing market, by increase your demand or by decreasing your demand, you can take the financial incentive because you contribute to the stability of the power grid. That's one opportunity. Another opportunity takes place in the spot market. So this is a process flow diagram of air separation unit, which is the most representative system in the case of the application of DSM. There is a main compressor that pressurizes air in order to separate this into nitrogen and oxygen. It consumes a huge amount of electricity in the industrial sector. So, given the fluctuation of the electricity prices, we can adjust the production level to this fluctuation in order to save the cumulative power cost, while satisfying a certain such as like purity criteria. So this could be another, the second opportunity to apply the DSM to the industrial sector. So on top of that, so in the academia at least, many people have tried to apply this DSM to various industrial plants, such as I already introduced, air separation unit, also chlor-alkali electrolysis is another representative kind of toy problem that has been investigated. Also, some investigated the application of DSM to desalination plant that changes the seawater to drinkable water. Also, the carbon capture plant was also another interesting target for the DSM study. Mostly, this was led by the researchers in Norway. So today's talk is mostly about the application of DSM strategy to three different electrolysis-based systems. So first one is not just a simple chlor-alkali electrolysis, but the one that employs the switchability between the two different operational modes. And second one is the electrochemical CO2 reduction system that converts CO2 into variable chemical products. Third one is water electrolysis that produces hydrogen, but this is really practical problem. So let me introduce these case studies one by one. So first work was done in collaboration with Professor Listos and also the industrial partner Covestro when I did my PhD postdoc in Aachen. So looking at this slide, so the conventional chlor-alkali electrolysis is based on this scheme. So we decomposes brine into chlorine gas, sodium hydroxide, and the hydrogen as a byproduct when you apply around the 3 voltage of the self-potential to this electrolyzer. This is the conventional way of making these chemical compounds. As an alternative, we could also replace the cathode sides by oxygen polarized cathode. Then with reduced self-potential around the 2 volts, we can produce the same amount of chlorine and sodium hydroxide. But the difference is that we need to supply extra oxygen as the raw material, and we don't have the hydrogen byproduct anymore. So looking at this graph, so for the same amount of chlorine production, this one, the conventional mode or the hydrogen mode, consumes around 33% more electricity than the other one, the oxygen mode. And my German industrial partner, they invented a novel cathode that employs a bifunctionality that allows us to operate this electrolyzer on both the modes. So here's a new idea. So what if we apply the demand side management by employing not only the simple, the flexible operation, but also the switching operation. So for instance, if the price of electricity is high, then we could reduce the amount, we could reduce the production level, but also we could switch our operation mode to the oxygen mode, and also vice versa, so that we can enhance the benefit of the demand side management through this approach. So our problem is, the goal of this program is here. So our goal is to analyze economic potentials of this switchover chloralkali electrolysis through optimizing both oversizing factor and also operation. So it's kind of an integrated problem. So this slide illustrates how this concept operates. So the electrolyzer can operate one of these three the most. And if you want to change your operation mode from this hydrogen mode to oxygen mode, we need to shut down our electrolyzer first and clean up with the nitrogen gas, because in the cathode chamber, if you don't do that, oxygen and hydrogen meet each other and it may cause explosion. So the industrial people never wants such an occasion. So that's why we need to stop by at this clean mode. That may take less than 45 minutes. And we should put the chlorine storage tank, because we should guarantee the constant supply of the chlorine to the downstream process. So these guys they are not interested in what we are doing in the front. They always require the stable supply of the intermediate products. But the thing is that chlorine gas is really very dangerous gas. Therefore, the capacity of the chlorine gas storage is legally limited. So the maximum duration for the storage of the chlorine is around 3 hours, according to my industrial partner. And also, we set this special constraint of minimum 6 hours of operation in one reactive mode. That means in a day, maximum 4 times of mode switching could take place. Because if the mode switching takes place too frequently, then the operator at the plant doesn't like that situation. So I formulated an optimization problem. So our goal is to minimize this hourly production cost. This is the sum of the operating cost saving and also additional depreciation cost. So the operating cost includes the cost of electricity and the oxygen and also the credit from the hydrogen byproduct. And this one is important, that's why I put the underline here. So depreciation cost. So this switching operation is, in order to employ this switching operation, we are not able to do with existing chloralkali electrolyzer. We should do something. We should do some retrofit. So that causes extra cost. So that needs to be included in this objective function. So there's no free lunch. And there are many constraints. So some are highlighted with the underlines. So these transition constraints are really important. So these constraints include some binary variables, of course, and also this production rate limit is influenced by this oversizing factor alpha. And here the alpha is an optimization variable too, which is independent of the time. Because as I told you at the beginning, my goal is to optimize simultaneously optimize the oversizing and the operation. So since this program includes some bilinear terms, so this program ends up with the MI and a P. So we are not able to solve this problem easily. Therefore, I applied the decomposition method. So I applied this method at this alpha function, and I solved the MIRT subproblem using sequence. So here are the key results. So I compared the two different scenarios. One for the 2017 scenario, the other one for 2030 scenario, which has been artificially generated. So for this moderate case, you can see that the optimization results tells us that demand side management or the switch, which is based on the flexible and the switch operation is not very advantageous because the extent of the fluctuation is not really strong. But in comparison, in contrast, in the year of 2030, we increased the average price of electricity, and also we tripled the extent of the fluctuation because we assume that in the year of 2020, this is a German case, the portion of the renewable energy resources in the power grid will be much bigger than the year of 2017. In this case now, this flexible and switchable operation looks very advantageous. So when the price of electricity is high, then it's preferred to operate at the high. If the price of electricity is low, then it's preferred to operate at the high pole, and also at the high level, and also vice versa. Also, the bigger oversizing is found compared to the 2017 case. Then the question is, if this is really beneficial, if we consider both operating saving and also additional depreciation. So I have created two extreme cases. The first one only requires the minimum cost for retrofitting the electrolyzer itself. The other extreme case is different. On top of the electrolyzer, we need additional cost to enlarge the capacity of the auxiliary units around the electrolyzer. Because we sometimes want to increase our production level. So that's why we need additional capacity. So this gray bar indicates the savings of the production cost. If this is positive, this is good for us. If you take a look at this right-hand side graph, this becomes negative. It means that the advantage, financial the improvement from the operating cost cannot compensate for the additional capital cost. So the key message from this case study is that don't forget the additional investment for the capitals if you want to employ the demand side management in the existing industrial plants. Okay, now let me move on to the next case study. This one was done in collaboration with Professor Misos. Now this one is fairly like the new technology compared to the chloralkali electrolysis because with the chloralkali, the guy is really traditional, one of the traditional chemical technologies. But this one, electrochemical reduction, is still at very low TRL. I would say it's around the TRL from the level 2 to 4. So the basic principle is that we reduce the carbon dioxide by utilizing, hopefully, the renewable electricity to produce valuable chemicals such as carbon monoxide, formic acid, ethylene, or ethanol. But the problem is this technology is that this is too expensive technology again. Because of the expensive materials, because of the expensive equipment, but the biggest cost driver is the power cost, electricity cost. Because of the huge, the overpotential. So there might be several solutions to overcome these challenges, but one of my solutions is to apply the demand side management to this novel technology. Why? If we can adjust the production level of this new system to the fluctuation of the electricity price, we could also expect some benefit, financial benefit. But here is some challenges. In the case of the chloralkali electrolysis, the selectivity, the product selectivity does not change well or when we change our power load. However, in the case of this E-filter case, the electrochemical reduction, selectivity of the product changes dramatically. So here, if we increase the power load or in terms of the current density, and here the target chemicals are syngas, the composition of carbon monoxide decreases while the composition of hydrogen increases. So if we change our power law, then the composition of the product will change. This is not a favor the situation. So the goal of this case study is to propose this ECO system configuration that enables flexible operation while keeping the product quality constant. That was our problem. So here's the basic idea of the idea that modularized this ECO system. This idea was motivated from conventional problem in the industrial engineering. It's called parallel machine scheduling problem. So this problem solves this kind of problem that includes the n number of identical machines. So how should we allocate our job to these vertical identical machines? So we propose this concept of the system configuration. So we divide the whole electrolysis system into small modules. And we make a decision, we make individual decisions. In this case, this guy could produce different amount of the syngas from the others. But we impose a constraint that the composition of this mixed stream should always satisfy our product quality constraint. So while the product quality is at a constant level, this total flow rate could be different. And so this configuration could enable the flexible operation while keeping the product quality constant. So here is a schematic diagram of this modular ECO system. So we supply carbon dioxide and water, and there are like n number of sub-modules that is comprised of electrolyzer and the CO2 separation unit that recycle the unreacted CO2. And then we put together, and there should be a certain storage tank that store the products and guarantees the constant supply of the product to the downstream process. So in this case study, we consider this simplified reaction stoichiometry that produces hydrogen and carbon monoxide with the ratio with the hydrogen to carbon monoxide molar ratio equal to 1, which is suitable for the Fischer-Tropsch synthesis. And also while we introduce several the conditions that characterize the oversize, number of stacks, single horizon, and so on and so forth. So there are some key assumptions. For instance, we assume that there is no side product, and also unreacted CO2 is completely removed. And also we only consider the power demand for electrolyzer only because that's the major energy consumer. Our objective is to minimize the power cost for the given time horizon. And there are several constraints that should be included, and I'd like to direct your attention to these first two constraints, which are nonlinear functions. So typically when you solve the scheduling problem, we linearize the nonlinear functions. But this time we try to solve the nonlinear scheduling problem as it is to guarantee the accuracy of the solutions. And also, in order to avoid an alternative solution that arise from this parallel machine scheduling problem, we add symmetry breaking constraint. And in order to solve this nonlinear programming, scheduling programming, we apply this wavelet-based grid adaptation algorithm, which was proposed by Professor Lissos, in order to gain the near optimal solutions. And this problem was implemented in Mango, the in-house deterministic global optimization solver. So here are the results. So as you can see here on the left-hand side, here we assume that there are 4 modules and their operation profiles are different. It means each module produces different the product streams. However, this red line tells us that the purity or the concentration of the mixed stream is at the constant level. And while doing so, the total power demand is fluctuating as we expected, which is good. So we found that we could save around like a 4.27% of the power cost. And also there is the issue regarding the CO2 recovery unit. Because if you recover CO2 by using like an army scrubbing, that unit is dynamically not fast. But if you use like a pressure swing absorption or membrane, such a unit is agile, more agile. So by assuming a different maximum ramping duration of this each modules, we could find out that the savings of the operating cost could be different. So this is end of the second case study, and let me be fast to cover case study third case study. So this case study is about South Korea. There is the biggest island called Jeju in the southern part of South Korea. This is a very beautiful city, and also it has a huge, the plentiful amount of solar and wind energies. In this island, the price of electricity changes frequently, and also, as you can see here, the hourly carbon footprint of this island changes all the time. So in the afternoon, in the morning and afternoon, the hourly greenhouse gas emission factor is decreased because of the generation of the solar energies. So if we calculate this emission factor based on the data in 2020, it's just to a 0.2662 tons of CO2 equivalent per kilowatt hour, which is just like 60% of the emission factor in the mainland. And also, the amount of the curtailed electricity in this island is getting increasing. So in year 2021, the total, the cumulative amount of the curtailment was 12 gigawatt hour, but it's increasing. So at the moment, there's one government research project ongoing in Jeju, which is to demonstrate the 12.5 megawatt green hydrogen production system. So they combine 4 different electrolyzers: PEM, alkaline, AEM, and SOEC. And they raise the question: can we produce a clean hydrogen at a reasonable cost using a water electric system, mainly powered by grid electricity? Do you think this is feasible? Maybe not. If you are aware of, if you are aware of how much electricity is needed to produce hydrogen through water electricity, and also if you are aware of this number of emission factor is not low enough to reach the green or clean hydrogen. Anyway, in order to achieve this goal, we introduced 3 different strategies. So, flex operation, and also we could use the curtailed electricity. We could purchase the credit from the renewable electricity 100 market. So we formulated an optimization problem to consider all of these 3 solutions to minimize the levelized cost of hydrogen. So this is a simplified schematic diagram of the water equation. This is not very special, but this is mainly powered by this connecting to the power grid. And here is an optimization problem, which is not special, it's an LP problem, but we calculated, let's say, the effective carbon footprint. So we consider the hourly data of the power trading in the Jeju, island. And this is the final slide of this presentation. So this is our base case. Here is our target area. So the levelized cost of hydrogen should be below the average sale price of hydrogen. And also there is a certain level of the carbon footprint which is required to be recognized. as a clean hydrogen. So by applying these three strategies, starting from this point, we could go up, go down, and we find two economical and environmental solutions, which is very close to this target area. And if the share of the renewable resources in Jeju Island will increase in the future, we believe that these 2 points will jump into the middle of this reason. So I'd like to conclude my presentation with some key findings. Also, I'd like to acknowledge my accounting sources, and also thanks to my students and my German collaborator and Korean collaborator. Thank you for your attention.